So hello everyone, myself Aman and my name is Anurag Mishra. So our topic is flow through annular region. We have some discussion regarding to. So first is today we will discussing a very interesting topic from the transportation phenomena, flow through an annular region. We study annular flow. This type of the flow heat exchanger, drilling operation, and even the blood flow in the artery. To develop the flow equations, we will use that the Navier-stokes equation in the cylindrical coordinates, apply boundary conditions, and finally get the expression for the velocity maximum and the average velocity angle. Okay, so Anurag, tell me that annular region, what is that exactly?
It's basically the space between two coaxial cylinders, like a smaller pipe inside a bigger pipe, and the fluid flows in the gap between them.
Okay, so the bigger cylinder has a radius r and the smaller one has the radius ar.
What is the ratio of the inner radius to the outer radius? So its value is between 0 and 1.
Okay, so got it. And what are we are trying to find in this topic?
The main goal is to find the velocity profile of the fluid. That means how the velocity varies with radial distance between the cylinders.
Okay, so alright, and I have noticed that we also calculate the things like maximum velocity and the average velocity too.
Yes, once we derive the expression for velocity, we can use it to get Vmax, average velocity, mass flow rate, and even the drag force on the wall.
Okay, nice. But before we start with the maths, are there any assumptions?
We assume that the flow is steady, incompressible, and laminar. And also we apply the no-slip condition and on both cylinder walls.
Okay, perfect. Now let's begin with the derivation step by step.
Flow through annular region. Before diving into the specifics of annular flow, let's briefly recap internal flow. Internal flow refers to the fluid motion confined within solid boundaries, like pipes or ducts. It's crucial in chemical engineering for designing equipment such as reactors, heat exchangers, and pipelines. Understanding internal flow helps us predict pressure drops, heat transfer rates, and optimize system performance. Now, annular flow specifically occurs in the space between two concentric cylinders. Some real-world examples where this is encountered are: first, double pipe heat exchangers, where one fluid flows through the inner pipe and another flows in the annular space between pipes. It's also seen in oil well drilling, where drilling mud circulates down the annular space between the drill pipe and wellbore, and in nuclear reactors, where coolant flows through annular fuel rods. So, understanding the behavior of fluid in an annular region is vital for designing and analyzing such systems. Next, let's define what an annulus is. Geometrically, an annulus is the region between two concentric cylinders. The outer cylinder has a outer radius RO, and the inner cylinder has an inner radius RI. The fluid flows in the space between these two cylinders. To visualize this, imagine a straw placed inside a larger pipe. The space between them forms the annular region where the fluid flows. Comparing this to flow in a circular pipe, where fluid is confined within a single cylindrical boundary, annular flow involves two boundaries. This additional boundary affects the velocity distribution and shear stress profile, making the analysis more complex. Understanding these differences is key to accurately modeling and predicting flow behavior in annular geometries. Before setting up the problem, we need to establish some assumptions to simplify our analysis following the logic presented in Transport Phenomena by Bird, Stewart, and Lightfoot. First, we assume steady flow, meaning the fluid properties at any point don't change over time. Second, the fluid is incompressible, so its density remains constant throughout the flow. Third, the flow is laminar, characterized by smooth, orderly fluid motion, typically occurring at lower Reynolds numbers. Fourth, we consider fully developed flow where the velocity profile doesn't change along the flow direction. This implies that the effects of the entrance region have dissipated. Fifth, the fluid is Newtonian, meaning the shear stress is linearly proportional to the shear rate. Sixth, we apply the no-slip boundary condition, which states that the fluid velocity at the solid boundaries is 0. Lastly, we assume constant viscosity and isothermal conditions, meaning the fluid's viscosity and temperature remain uniform throughout the flow. These assumptions allow us to derive a manageable mathematical model for the velocity distribution in annular flow. With our assumptions in place, let's set up the problem using the Navier-stokes equations in cylindrical coordinates. The Navier-stokes equations describe the motion of fluid substances in cylindrical coordinates r, theta, z, and under our assumptions, the axial component simplifies to 1 upon r d by dr of r dvz upon dr is equal to 1 upon mu dp upon dz. Here Vz is the axial velocity, mu is the dynamic viscosity, dP by dz is the pressure gradient along the axial direction. This simplification arises because under steady fully developed and axisymmetrical conditions, the velocity component in the radial Vr and angular V theta directions are 0 and there are no variations in the angular and axial directions. To solve this differential equation for Vz of r, we integrate it twice with respect to r, introducing two constants of integration. Applying the no-slip boundary conditions at r equal to ri, Vz equal to 0, at r equal to ro, Vz equal to 0, we can solve for these constants. Substituting the constants back into our general solution gives us the velocity distribution for laminar flow in an annular region. The velocity profile helps us understand how fluid moves between the two cylinders and is fundamental for further analysis such as calculating flow rates and shear stresses. Conclusion. In this segment, we have established the theoretical foundations for laminar flow in an annular region. We have defined the geometry of an annulus, discussed key assumptions, and set up the problem using the Navier-stokes equations in cylindrical coordinates. Understanding these concepts is crucial as we move forward to derive the velocity profile and explore related parameters like maximum and average velocities, mass flow rate, and drag force.
It is called as a cylindrical coordinate. Now, cylindrical coordinate origin. This will go as an r-axis and this will go as an z-axis. Now, flow through an annulus, we will see that non-vanishing velocity will be as vz. What will be the velocity? Vz. Vz will be our velocity. This will be the z direction. This moving forward to the z direction. This is the r direction. Lights r direction, and this is moving forward. So this, remember this, that cylindrical coordinate origins. So this will be your origin. This point is your origin, and this is the non-vanishing velocity, which we termed as a vz. Now moving forward, so here we shown that when the non-vanishing velocity vz is here, while moving forward, like simply flow through an annulus as a cylindrical region, the cylindrical coordinate as given in the origin. So cylindrical coordinate is given in the origin, like 0 to 0, like we could say, okay, this is in the z direction and this is on the r direction, okay, and it is moving toward the down from downwards to upward. This is moving from downwards to upward direction. Please remember this. Okay. Now the non-vanishing velocity is given as a vz. So how it will the answer is vz is equal to vr. This is the answer. V0 is equal to vr is equal to 0. This is also there. And non-vanishing velocity is equal to vz in the origin. Then moving from the z direction, r. So this is that. Okay. So this is that non-vanishing velocity. This is on the z direction on the r. Okay. Should I repeat this? So okay, now I will repeat this once more. This is the origin. 0, 0. This is z. This is r. This is moving toward the upper direction. So this is just moving toward the upper direction, and while this is moving toward upward direction, then the velocity vz is given. That's cylindrical coordinate at coordinates. P is equal to pz directly. We will consider as a P is equal to pz. Okay. Due to pz, V is equal to PR, condition velocity is and this. Okay. So I think you got all these points which I told you. Now the main thing is the inner radius we consider as an here. This is called as inner radius. Okay. Inner radius. And this is called as outer radius. This is called outer radius. Now you know that just like in previous slide we had seen that it's showing that it is moving from upward to downward direction. Downward to upward direction. Here is downward to upward direction, and for inner radius this is for outer radius. Okay. Now where should be the velocity vz? Velocity vz should be given here and here too. Velocity vz will be given in the both direction. Please remember this. Velocity vz will be in this both. Here also it will be 0 and here also it will be 0, and then here will be the points. Here will be the trace of the points, and here also there will be the points in which we will consider, but here it is going as a vz is equal to 0, but here it will go as vz is equal to vz max. Okay, please remember it will go as a vz, and this will, as we all know, this is called as the inner radius and this called will be as the outer radius. Okay. So v is equal to vz. Now here also some complexity is there, like what could I say that here also some complexity is there. What will be the this length? Okay, just tell me what will be the this length. See, simply we called as an inner radius. Okay, we called as it inner radius. We called it as an outer radius. You all know that this called as an outer radius. Okay. Just a second. Sorry. This we call as an outer radius. This we call as an inner radius. What we will call this? What we will call this? I'm asking this. Okay, and let me tell you what we will call this. This we called as an wavelength R. Okay, this will be called as a wavelength R. Okay, this is called as KR. This is called as wavelength KR, and this is called as R. Okay, got it. Now what this called as? This called as a momentum flux. This called, what we call this? We called him as a momentum. We called it as simply as a momentum flux. Momentum flux. This region, please remember, this one region we call as a momentum. So I think you got all these points. So these are the points here. This we will call as a node, then we will consider it as this one. Okay, I already mentioned here. So I already just solved that question. See, wherein R is given here, KR is given, Vz is equal to Vz max. Okay. This called as a momentum flux. Okay, so I think you must all got this. Now the main important thing is which we need to be is that velocity distribution. Now we all have discussed it already. KR, KR, R is called as a momentum distribution. Okay, it's called we call as a momentum distribution. This already we call as the momentum distribution. This we call as velocity distribution, and this we call as the shear stress of momentum and the flux distribution. See, in the flux, it is given as kr. This is for the inner radius. Okay, this is for the outer radius, and this is z for the origins point. This is r, and this is on the z direction, as we already said. Now the just see the surface of the zero momentum flux. We will see the surface of zero momentum flux. Okay, we are going to see that, not we are going. So this we will consider as a plus direction. This we will consider as a minus direction. Okay, this is moving in the upward direction. Okay, mostly velocity distribution, this is going in the upward direction, and this also is going toward the upward direction. Okay, and this is also in the plus direction, and this also will be in the minus direction. And what is this? This is the surface of the zero momentum flux. Okay, this is called as a surface of an zero momentum flux. Okay, so yeah, as we all know that this is the momentum flux. Okay, you already remember this, that this is the momentum flux. Okay, you know that this is the momentum flux, don't be confused. And this is the Vz is equal to Vz is equal to Vz max, and this is the Vz is equal to Vz max. Okay, and what is this? What about this region? What about this region? These both regions. Okay, just see that, just see and explain this. So this will be the, what will be the Vz is equal to V0. This is called as Vz is equal to simple as that. Okay, simple as that. Okay. So let's move forward to the next slide. See what we are considering here. We considering here as a r. Okay, here we go. So this we consider it as an r. Now we are considering it this as a r plus delta r, and this position, okay, please remember this called as an delta r position. Moving upward, okay, this we called as an delta r position. You got it? This we call as delta r position, and this delta r position. Okay, so let me just revise you all this thing once again. See, this is moving from the upward to upward side in the cylindrical. This is we just moving from downward to upward side cylindrical. Okay, and this is the momentum flux. Let me remind you, this is called as a momentum flux. Okay, the flux. Okay, okay, and this we called as this as a Vz is equal to V max, equal to V max, and this we call as a Vz is equal to 0. Clear? What if this we both as consider it as an Z is equal to 0. Okay. This is for the, actually please remember this, not, this is not for now inner radius, that is for the inner radius. For the inner radius it is given here as AR. Okay, for inner radius, and for outer radius it is given as an R. Okay. And for particular disease, okay, for only for this reason we consider it as an wavelength R. Okay, so thank you. So here we stop.